In this video, we're going to conclude our study of wave motion. Specifically here, we're going to talk about the equation that describes a wave traveling down a string, and we'll also talk about what we mean by a standing wave and how standing waves are formed. So let's look at the equation that describes a traveling wave. We actually have two different ones, depending on whether the wave is traveling to the right or to the left. You'll notice the only thing that differentiates these two is whether it's a minus sign or a plus sign in the formula. The first thing we want to understand is, what do these equations actually allow you to calculate? So here we've got a picture of a traveling wave, and what we're plotting here is y versus x. In other words, that is a picture of the wave at one particular time. Okay? So this is not position versus time, it's position versus position. So what our equation allows us to do is to calculate the displacement from equilibrium, y, at a given position along the string at a particular time t. So for example, if I wanted to know what is the position of the string at this point x along the string at a time t, I would plug in that value of x, the time that I want. That's what would go in, and what the formula would allow me to figure out is that the y position of the string is right there. Okay? So that's what the formula allows you to do. It allows you to find the displacement from equilibrium of any point along the string at any particular time t. Remember too that a traveling wave is always moving. So if I were to look at this wave a short time later, what we would find is that the wave would have shifted to the right by a certain amount. If the wave is traveling to the left, then we simply use this equation instead. Now, let's look at what omega and k represent in these two equations. Omega is the one that you already know. Omega is just 2 pi over the period, or 2 pi times the frequency. And remember, in simple harmonic motion, we called that the angular frequency, and we do the same thing here. So that's still angular frequency, and notice that the units of omega are seconds to the minus 1. We don't use hertz because we use hertz, or we reserve that for regular frequency. Now k is something that you haven't seen before. K is referred to as the wave number. Notice that since the wave number is defined as 2 pi over the wavelength, it has units of meters to the minus 1. The first important thing to know about k is that it has nothing to do with spring constants. And obviously that's not hard to understand because there's no spring in this problem. But in simple harmonic motion, k is the spring constant. Here, k is a completely different meaning, so don't get confused by that. It's one of those times in physics where we use the same letter to mean something different. You'll notice that the purpose of k is the same really as the purpose of omega. If I want my wave to be periodic in time, then omega has to be defined as 2 pi divided by the period. If I also want it to be periodic in space, then k has to be 2 pi divided by the wavelength. Remember, anytime we want a sine or a cosine to be periodic over something other than 2 pi, we simply take 2 pi and divide by the thing we want it to be periodic over. So in a wave, we have it's periodic both over a distance, the wavelength, and over a time, the period. One other note about these equations. If you look somewhere else on the internet or in a different textbook, you may see these equations written with a sine instead of a cosine, and that's certainly equally valid because really the only thing that differentiates a sine from a cosine is where the wave is at t equals 0. For this course, I'm going to just use cosine, but don't be surprised if in other courses or other places you see it written as a sine. Let's go ahead and try out this formula. A wave is traveling on a string to the right with a velocity of 20 meters per second. The frequency of the vibration that created the wave is 297 hertz, and the amplitude of the wave is 0.050 meters. What's the wavelength of the wave, and what's the displacement of the string at a point x equals 0.35 meters along the string at a time of 2 seconds? Why don't you pause the video and do this on your own, and then restart the video and see if you did it correctly. Okay, so the first thing is, of course, we need to be in radian mode. No degrees here, so if you were in degree mode, you definitely didn't get the second part of the question right. Let's start out with figuring out the wavelength. You'll notice that we know the speed of the wave and the frequency, and therefore we can calculate the wavelength. Wavelength is velocity divided by frequency, since we know that velocity is wavelength times frequency. And therefore we get 20.0 divided by 297. Notice that both of those values have 3 sig figs, and so we get 0.0673 meters for the wavelength. Once we've got the wavelength, we can figure out the displacement of the string at a certain point along the string and at a certain time. That's what this equation does, and I don't have to write in the comma or parentheses x comma t. That's just to remind you it's a function of both, but I'll just write y is equal to a cosine of kx minus omega t. And at this point now we just have to plug in the correct values. Remember, a is the amplitude, so we were told that the amplitude was 0.050 meters. Then we've got the cosine of k. Remember, k is 2 pi over the wavelength, so 2 pi divided by 0.0673 times x. Now, x is the position along the string where we want to know the displacement, so that's given here, 0.35. Then we want to subtract omega t. Again, omega is 2 pi times the frequency of 297. And then we want to know this at a time of 2 seconds. And so we put the 2 in there, close our parentheses, and that's what we want to calculate. Again, calculator needs to be in radians. The value that you should have gotten was the y displacement of the string was 0.015 meters. Obviously, the maximum value of the displacement is the amplitude, and so this is something less than that. Let's talk about the superposition principle. It says when two or more waves pass through the same region at the same time, the displacement of the medium is the sum of the individual displacements of the waves. So we're going to look at this in some detail for waves on a string, but I want to talk about a conceptual example first. Imagine that I've got a person over here and a person over here, and they're both talking. And now I've got another person in the middle. So for this person, the waves from both of these people are simultaneously arriving, or it doesn't have to be simultaneously, but the waves are arriving at that person's ears. Well, you'll notice if there are multiple people talking in a room, you have no problem hearing all of those conversations simultaneously. The reason that that works is simply that the waves add up, so that one person's wave and the other person's wave just add up, and your brain therefore hears both waves simultaneously. So that's really all the superposition principle is talking about. One of the other interesting things about waves is that at a moment in time and a place in space, they add up, as we're saying here. But also they're just continuously passing through each other. So in other words, it's not like one person's wave blocks the other person's wave from coming through. It's not like a collision between particles where if I've got a particle coming in like this and another particle coming in like this, they're not going to pass through each other, they're going to bang off each other. But waves just pass right through. So it's a really interesting thing. But at any moment, if two waves are present, then in that region of space, they simply add up. Well, let's look at the details of what we mean when I say that the waves just add up. It turns out that at any moment in time, I can get what we call constructive interference or destructive interference. In this case, these are momentary things. So let me kind of describe what I've got on the page so far. Here I've got two wave crests that are traveling towards each other. Now, what I want to look at is what happens when they are right on top of each other, when they occupy the same space. Well, the superposition principle says that I just add the two waves together. So in other words, when they're directly passing each other, what I would see on the string is the combination of those two waves. That's what we mean by the superposition principle. But after the two waves pass each other, they just look like they did before. In other words, we get constructive interference, meaning we get a bigger displacement right here because the waves add up. But they don't permanently affect each other. The waves just keep going in their own way after they pass. Okay, let's say that we've got a crest going one direction and a trough coming the other way. Well, what's going to happen on the string when those two are directly passing each other? Well, the answer is you're not going to see anything momentarily on the string because they're going to cancel each other out. And that's what we mean by destructive interference. Notice, though, again, it's just a temporary thing because after they pass, they look as if nothing happened. So our crest keeps going to the right, our trough keeps going to the left, and we only got that destructive interference for that moment they passed. Again, simply because we find that waves just add as they pass each other. There's a really interesting application of this basic physics, and that's the concept of noise-canceling headphones. I took a picture of some Bose headphones here because Bose was kind of the first manufacturer that really got into this idea of creating noise-canceling headphones. Some of you might own some noise-canceling headphones, or you may have tried them, even if you don't own any. I don't own any myself, but I've tried them out, like in Best Buy, and it's pretty cool. You put them on, push the little button to activate them, and all of a sudden you can't hear the background noise of the store at all. And then, of course, if you put music into them, then all of a sudden the music sounds great because you're not hearing any background noise. Well, I want to show you how this works. So normally, if you think about it, when the speaker in your headphones is sending music into your ear, the problem is that even if you have closed headphones design like this, some noise is still getting through and also getting into your ear. And what we'd like to do is maximize the sound coming out of the speaker and get rid of the noise coming in from the environment. So here's what noise-canceling headphones do. They actually have a microphone on the outside, and you probably don't notice it. It's usually just a small hole. But what the microphone is doing is it's taking in the sound from outside the headphones. So let's say, just to keep it simple, the sound outside the headphones is a sine wave that looks kind of like this. The next thing that the electronics in the headphones do is they take that sound wave and they invert it. So in other words, now the sound wave looks like this. Then it takes the music that you're playing and adds to it the inverted sound wave from the outside noise. So now what's coming out of the speaker and going into your ear is actually the music and an inverted version of the noise. But now coming directly into your ear around the headphones is the original noise. But what happens if you take this wave and you add this wave to it? They cancel out. And so ultimately, the sound that goes into your ear is the combination of the noise, the inverted noise, and the music. And so the noise cancels out, and the only thing you hear is your music. And so your headphones, your noiseless headphones, are doing that continuously, taking the signal coming in from the outside, inverting it, and adding that to the source of music that you're actually trying to listen to. So it's a very cool idea of continual destructive interference. What would happen if we send a traveling wave down a string, which is then reflected from a fixed end? Well, first of all, if I send a pulse down a string and it hits a fixed end, that pulse actually gets inverted on the way back. So we need to know that much. Okay, so a pulse or a wave in general gets inverted when it gets reflected from a fixed end. But the question here is saying, what if I send a continuously traveling wave down here? In other words, instead of just sending a pulse, I'm sending a continuous wave down the string, and that wave is being reflected at the end. What's going to happen? Well, one way we can look at this is mathematically. In other words, we know what the equation is for a wave traveling to the right, and we know what the equation is for a wave traveling to the left. So since our wave is being reflected here, what we're going to have is the combination of a right traveling wave and the reflected wave, which is a left traveling wave. Now, the only thing that might seem a little odd here is, so here's my right traveling wave, my left traveling wave. You might wonder why it's minus instead of plus there. And the reason is simply from what I mentioned up here, and that is because the wave gets inverted, I have to put a minus sign here to acknowledge that the reflected wave is actually upside down of what it would normally be. Okay, so mathematically, that would be the answer, that what we would get is simply the sum of those two different waves. Now, that expression doesn't really tell me much, but it turns out that there's a way to dramatically simplify that. And you might try this on your own. If we use this trig identity, we can rewrite both of these terms. And by the way, if you look up a trig identity in a table or on the internet, it'll look like this. The plus or minus and the minus plus there, if you've never seen that notation, it's basically saying if you want to rewrite cosine of A or alpha plus beta, use the minus sign. And if you want to rewrite alpha minus beta, use the plus sign here. So that's what that notation means. So you can see that we could rewrite this term and we could rewrite this term using this formula. If you do that and then you go ahead and simplify your result, what you find is that this equation simplifies to this. What's interesting about that is that you'll notice now the time and the space terms are separated out from each other. They're no longer in the same argument of sine or cosine. So let's take a look and see, what does that tell us? What does that really mean? Well, it turns out it means that we get a standing wave. And so let's see why we get a standing wave. Again, what are we doing here? We're sending a traveling wave down a string. It's being reflected and coming back, so we've got the combination of two waves on the string. And we've seen that mathematically, this is the formula that describes what we see. I also just mentioned that what's interesting about this is that the time and the space are now separated out in different arguments. So let's see if we can figure out what that would mean. The first thing I want to do is I want to just graph this part of the equation, 2a sine kx. Well, what does that look like? It's a sine wave, so I know a sine looks like this. And then the other thing I know is that, remember, k is 2 pi over lambda, so it's periodic over lambda. In other words, that would be lambda, 2 lambda, etc. Okay, so that's what that would look like, and of course this would be 2a and negative 2a. Notice that this point and this point and this point and this point and this point are always going to be 0 because this part of the function is always 0 at those points. But now let's think about, what does sine omega t do as time is going along? Well, notice that it's basically going to be varying between a value of -1 and a value of 1, right? That's what this will do. It's just going to oscillate between 1 and -1 as time goes along. So to picture what this would look like as time goes along, well, when it's equal to 1, it would just be the curve I've already drawn. What would it look like when it's -1? Well, it would be the same curve, but flipped. How about if it's some value between 1 and -1? Well, we'd just be multiplying either of those curves by a smaller value. It wouldn't change where our zeros are. In other words, the string might look like that at some point, might look like that at some point. Of course, it could even be 0 at some point when sine omega t is 0. And so what we would see is that our wave no longer travels. In other words, it's not like this hump continues to move to the right like it does in a traveling wave. This point never moves, and neither do these maximum points. The string is going back and forth, but those points are always the same as well. Those places where the string is moving a maximum amount we call antinodes. And the places where the string doesn't move at all are called nodes. And so we call this a standing wave because now we no longer have movement along the string. And you'll see this in lab. It's really kind of a cool looking thing that the string is just vibrating back and forth. At the antinodes, it's vibrating a maximum amount. At the nodes, it's not vibrating at all. So that's what a standing wave is. Notice that we get a standing wave when we simply have a right traveling wave and a left traveling wave passing each other on the string. Let's use what we've learned about standing waves to look at the particular case of a string with two fixed ends. The reason this is an interesting case is if you think about any stringed instrument, whether it's a guitar or a piano or a violin, all of those instruments are made up of strings of fixed length where both ends of the string are fixed. And so the question is, what possible standing waves can occur on a string with two fixed ends? Well, I've got some pictures here of some of the waves that can occur. Because both ends are fixed, we know that we've got to have a node at each end of the string. Now, other than that, we can have multiple other nodes. So the simplest standing wave we could get is one where there's just one antinode and the two nodes at the end. But then we could have two antinodes with an additional node in the middle, three antinodes, four antinodes. So we can develop these different patterns, and we could keep going with that. So let's see if we can figure out what the relationship is between the wavelength that is on the standing wave and the length of the string. You'll notice the length of the string, I'm going to use L. So here's the length of the string. And you'll notice that in the first case, since we know a wavelength looks like that, in that first case, L is equal to lambda over 2. In other words, there's half a wavelength on that string. In the next case down, you'll notice that L is just equal to lambda because there's one wavelength on that string of length L. In other words, again, one wavelength. For the next one, you'll notice that there are 3/2 of a wavelength on the string. And for the next one, there are 4/2 or 2 wavelengths on the string. Well, we can now come up with a formula that will calculate those for us. What we do is we say that L is equal to n lambda over 2, where n can equal 1, 2, 3, etc. And you'll notice that n is the number of antinodes. So in the top, we only had one antinode, so we would get lambda over 2. For the second case down, we had two antinodes, so we would get L equals lambda, etc. Okay, so n is the number of antinodes. It's also, as we'll see, the number of the harmonic, and we're going to talk more about that in just a second. Now, it turns out that it's useful to rewrite this formula in terms of the wavelength. So I'm going to write lambda is equal to 2L over n. And sometimes we put a little n subscript on lambda just to indicate, the first wavelength, second wavelength, third wavelength. In other words, what the wavelength is in each of these cases. Let's take that information that we just determined. So here's the formula we just figured out for the wavelength. And what we want to do is figure out what frequency would be present for each of these standing waves. In other words, what frequency would the string vibrate with? Now, of course, we care about this because, as we've said, this is how stringed instruments work, and we know that for an instrument to work, it's got to produce particular frequencies. And so we can actually figure out what those frequencies are. Starting with V equals F lambda, let me rewrite that as the frequency is equal to the velocity divided by the wavelength. Remember that for a wave on a string, the velocity can be written in terms of the tension in the string and the mass per unit length. Also, we know that the wavelength can be written in terms of the length of the string and the number of antinodes. So let's combine those two things. V is the square root of ft over mu, and then I'm dividing that by lambda, which is 2L over n. And so if we flip that around, what we get is F is equal to n over 2L times the square root of the tension divided by mu. And again, sometimes we put a little subscript n there just to say that these are the possible frequencies that would be created by a standing wave on a string. So in other words, notice that what we're saying is this pattern would produce the frequency if I put in n equals 1. This pattern would produce the frequency with n equals 2, n equals 3, n equals 4. And these are the harmonics. So this is the first harmonic, second harmonic, etc. Okay? And so remember, simple harmonic motion, I told you that harmonic related to music. Well, here's where it is. That what we find is if we start a string vibrating, it can vibrate at these different frequencies, which we call harmonics. And the first harmonic is simply the lowest frequency that the string can vibrate with. So here's the question. If I go ahead and pluck a guitar string or strike a piano string, which of those frequencies is the string vibrating with? Right? Because we've said if I've got a string with a particular length, it could vibrate at any of these possible frequencies. So what's it doing? Well, it turns out it's vibrating with all of the frequencies simultaneously. So when you hit a guitar string, you're hearing the first harmonic and the higher harmonics all at the same time. And what's interesting about this is it's the relative strength of those different harmonics that gives an instrument its unique tone. So you think about, why does a piano sound different than a guitar? They're just strings. Or why does a violin sound different from a guitar? Well, because of the construction of the body and everything else that goes into the instrument, one instrument will favor certain harmonics over another. And therefore, each instrument has a unique sound to us because of all of the harmonics that are present. Now, what's interesting for we humans is that what we perceive as pitch is the first harmonic. So in other words, our brains take the lowest frequency that's produced and say that's the pitch. And all of the other harmonics that are present just change the way we think about the overall sound. So that's how it actually works. I want to look at this formula that we figured out and just talk a little bit more about it. For those of you who play a stringed instrument, especially something like a guitar or a bass or violin, cello, etc., you know that when you want to increase the pitch of a string, you tighten the tuner. So notice that now it makes sense why that is, because the frequency is related to the tension in the string. Increase the tension, all of the frequencies go up, including the frequency of the first harmonic. You'll also notice that the frequency is inversely proportional to the mass per length. Now, one of the things, if you think about this from an engineering point of view, if you've got a string, you can't just have one string that's going to work from very low frequencies to very high frequencies, because the tension would have to vary too much, from not being tight enough to have the string make any sound to being so tight that the string breaks. And so what we find on stringed instruments is the lower strings are going to be thicker, because that's one way we can have enough tension to get the frequency we want. We need a thicker string. On the other hand, to get higher frequencies, we want thinner strings so we don't have to have them at too high a tension. And so just looking at that formula, you can understand why it is that on the lower notes of a guitar, the strings are thicker, on the top, they're thinner, and that it all works in that way. Why don't you go ahead and pause the video and do this last example. Okay, the lowest string of a guitar vibrates with a first harmonic frequency of 82.4 hertz. The length of the string is 0.648 meters. If the mass per unit length of the string is 0.00057 kilograms per meter, what is the tension in the string? So we've derived this formula that the frequencies that are present on a string with two fixed ends is n over 2L times the square root of the tension divided by the mass per unit length. Remember that n is the number of antinodes. So the first harmonic, remember first harmonic is n equals 1. And so we've been told that the first harmonic is has a frequency of 82.4 hertz. We're trying to figure out the tension, so let's go ahead and take this equation and do what we always do, which is solve algebraically before we plug in numbers. Don't forget that. We always are going to do that. Here I'm specifically talking about the first harmonic, so I'll just write F1. We know n is equal to 1, so I'll just write 2L, 1 over 2L, times the square root of ft over mu. I'm going to square both sides. F1 squared is equal to 1 over 4L squared times ft over mu. So ft is equal to 4L squared mu F1 squared. And now I can just go ahead and plug in the values. We get 4 times the length of the string, which is 0.648 squared, times 0.00057 for mu, times the first harmonic frequency, which was 82.4, and we've got to square that. If you solve for that correctly, you should have gotten 6.5 newtons. And you'll notice here we only had 2 sig figs, so we should have 2 sig figs in our answer. Okay, that ends this video on the basics of waves. We're going to be using this basic information as we go into the next chapter and look at reflection and refraction for light.